You have probably heard of the Rutherford scattering experiment from your high school classes. So in this video, we're going to dive deeper into the experiment and actually discuss how he actually figured this out and revolutionized our understanding of an atom. So without further ado, let's get into it. Basically, through this scattering experiment, he was able to discover that an atom is mostly made up of empty space. It has a tiny nucleus in the middle that is dense and positively charged. We've all seen this diagram in our textbooks probably, right? But usually the only thing that's explained to us is that some particles pass straight through while a few bounce back after hitting the dense nucleus. From that, we are just simply told that an atom has a densely packed and positively charged nucleus. But the full story, it's a little bit more complicated than that. So in the actual experiment, Rutherford and his team set up a thin gold foil only about 0.00004 centimeters of thickness, or around a few hundred atoms thick. Think about that. And gold was specifically chosen because of its high malleability. And the gold foil was placed at the center of a circular detection screen that was coated with zinc sulfide. And that was basically done so that the screen would produce tiny flashes of light when struck by alpha particles. And the alpha particles came from a small amount of radium that were placed in a lead box with a tiny hole in the front, which produced a beam of alpha particles. The entire apparatus was placed in vacuum to prevent the hindrance that may be caused in the scattering and stuff by air molecules. And finally, what they found was that 1 in 8,000 of those alpha particles bounced back at very large angles. Here's where things get interesting though. The most accepted atomic model till then was J.J. Thomson's model that was called the plum pudding model, in which he said that an atom is made up of a positively charged gas-like cloud, and inside of that cloud resided the electrons. But if that was true, then all of the alpha particles would have just passed straight through without much deflection. And according to Rutherford's calculations, the deflection experienced by the alpha particles would be close to negligible because they would be less than 1 degree. Maybe J.J. Thomson is wrong, right? So then he spent 2 to 3 years of his life searching for an answer to this phenomenon. Some of those alpha particles did hit the center of the atom, which we know today as nucleus, and rebounded, making a 180 degree of scattering angle. And that shocked Rutherford as well as his colleagues. So from this experiment, he put forward 3 major formulae. So they were the impact parameter formula, the distance of closest approach, and the scattering formula of Rutherford. Before we get into what these formulas are and get into a more deeper explanation, let's first see some of the assumptions that were made by Rutherford. The alpha particles pass in a hyperbolic path with the nucleus at one of its foci. Alpha particles can be considered as point charges. Scattering is due to only the electrostatic repulsive force, and it also assumes that the nucleus is stationary and considers the recoil negligible, and it also assumes that the size of the atom is much greater than the particle. The impact parameter. Let's get into that. We just need to understand first of all that the alpha particles don't just bounce off in straight line. Rather, they follow a curved path, specifically hyperbolic paths referred in the assumption. So this happens because of the repulsive force between the positively charged protons in the nucleus of the gold atoms and the positively charged alpha particles that we are firing at them. This repulsion is described by Coulomb's force, which has a formula through which we can calculate the repulsive force between 2 particles. It was also shown by Newton that any particle acted upon by a force that allows the inverse square law, for example, gravity or electrostatic force, they will follow a conic section path. Okay, so what the hell is this conic section path? Conic section path just basically means those shapes or paths that you get when you slice a cone in different ways. Those shapes are parabolas, hyperbolas, and the ellipses. Why do we say that it would travel in a hyperbolic path? Why not ellipse or parabolic path? So the reason behind it is there's something called escape energy. That is, the escape energy is the energy that is required to escape any other force that may be acting on that particle. If it had to travel in an elliptical path, it should have an energy that is less than 0. And if it had to travel in a parabolic path, it should have an escape energy that is equal to 0, which just means that it has just enough escape energy to escape that force. But in the case of our alpha particles, though, they are very high energy particles. They have more than enough energy so to escape the force, and so it has an energy that is greater than zero. So from that he figured out that particles would have a hyperbolic path. So moving on, and when he linked all the properties of a hyperbola to the physics of an alpha particle, he discovered that the asymptotes of the hyperbolic path is the path the particle would take if there was no repulsive force, also known as its initial path. An asymptote is basically a line that comes closer and closer to hyperbola but does not touch it. And when we draw a line from the nucleus or the center to the asymptote of the hyperbolic trajectory or the hyperbolic path, this line would be called the impact parameter, and this is usually referred to as B or P. And now you may be wondering, it is one of the formulas that he proposed, but how did it help him? What is this formula anyway? He is doing all this work to propose an atomic model. He has a formula to calculate B. B is the impact parameter, or how offsetted the particle is from the center or the nucleus. And it is important because it influences the value of Q, which is the distance of closest approach. So what is this distance of closest approach? Well, this is just how close the particles would come to the nucleus before they get deflected. How did he even figure out that the impact parameter influences Q at all? During a head-on collision, the particle is traveling towards the nucleus due to its initial kinetic energy, and then all of its energy gets converted into potential energy, which is fractions of a second. At that point, everything is potential, right? And this potential energy again gets converted back into kinetic energy when it returns back or when it rebounds. That is the actual concept that he used to derive his formula for Q, where he found out the impact parameter also plays a role. Another concept that he also utilized is the energy conservation. As I said, the kinetic energy gets converted into potential energy, and that gets converted back into kinetic energy. Initial kinetic energy and the potential energy, let's say that is the total energy. So that total energy should be equal to the other kinetic energy. So that is just because of the law of conservation of energy that we are all familiar with. First of all, he calculated the total energy, which is U, which is the potential energy, plus K of E, which is the kinetic energy. And that equals total energy. And this total energy is equal to K of alpha, or the kinetic energy of the alpha particle when it rebounds. So using this logic, he derived this formula. But all we need to understand is this is the formula to find Q. How does this even remotely connect to the actual model of an atom, let alone the nuclear radius? Based on his calculations on Q, which came out to be in the ballpark of 10 raised to minus 14 meters, he was able to get an upper limit for nuclear size. Because the distance of closest approach Q represents a point where the alpha particle's initial energy is completely converted into electrostatic potential energy or potential energy, causing it to momentarily stop and then reverse direction. So since the alpha particle doesn't penetrate the nucleus at this distance, the actual physical size or the radius of the nucleus must be smaller than the calculated Q. That's it. And due to the fact that the particle gets repelled, in addition to the fact that alpha particles are positively charged particles, he figured out that the nucleus had to be densely packed positively charged particles. Only then would it be able to repel the actual alpha particle, right? That's how he figured that the entire positive charge is concentrated into the tiny nucleus at the center. So he found out that the rebounding of the particles could only be possible if the plum pudding model of Thomson, again, is wrong. Groundbreaking at the time.